Hello my dear students, hi to all. This is ARJUN MEDIKURTHI and in this episode now we are going to discuss about one of the important chapter from our 10th class syllabus, that is the structure of an atom. So in this chapter we are going to discuss about the structure of an atom and the different types of theories that helps us to understand about the structure of an atom. So here the basic definition of an atom is an element is usually made up of a very smallest or a tiniest particle called an atom. So what is meant by an orbital? An orbital can be defined as the region of space where the probability of finding an electron is maximum. Probability of finding an electron. So probability means the chances to find an electron around the nucleus, which means an electron will be present outside the nucleus at different spaces, and here the space where the probability of finding an electron is maximum is usually known as orbital. So here in this chapter we are going to learn about the different types of quantum numbers, and those quantum numbers may help us to understand about the size of an orbit and the shape of the orbital and the orientation of the electron around the nucleus and the spin, which means whether the electron is moving in clockwise or in anti-clockwise direction. So here there are four different types of quantum numbers. The first type of quantum number is principal quantum number, denoted by small letter n, and the second type of quantum number is azimuthal quantum number, which is denoted by small l, which is also known as angular momentum quantum number, and the third type of quantum number is magnetic quantum number, which is denoted by ml, and the fourth one is spin quantum number, which is denoted by ms. So among four different types of quantum numbers, now we are going to discuss about the first type of quantum number, that is principal quantum number. Principal quantum number was described by a Danish chemist, Niels Bohr, and this quantum number was denoted by the small letter n. So the values of a principal quantum number starts from 1, 2, 3, 4 and so on. So this quantum number mainly explains about the size and energy of orbit. Energy of orbit. First orbit, second orbit, third orbit, fourth orbit. So if you observe the size of the orbit is steadily increasing from the nucleus. This is about the first quantum number. The second type of quantum number, that is azimuthal quantum number. So azimuthal quantum number was proposed by Sommerfeld. It was proposed by Sommerfeld, and azimuthal quantum number was denoted by small l, like, and here also l values starts from 0, 1, 2, 3 and so on. The azimuthal quantum number, which is also known as angular quantum number, proposed by Sommerfeld, explains about the shape of the orbital. Let us come to the diagrammatic expression. Here, if you know the n value, then it will be very easy to calculate the L value, followed by a formulaic expression L equals to n minus 1. L equals to n minus 1, which means if you know n value, so for example if n equals to 1, then L equals to n minus 1, which means L will become 0. L 0, 1, 2, 3 and so on. Here 0 is nothing but s orbital 1. If L equals to 1, then the given orbital is p. If L equals to 2, then the given orbital is d. If L equals to 3, then the given orbital is f. So azimuthal quantum number explains about the shapes of the orbital. The shapes of the orbital. We are going to learn about the third type of quantum number, that is magnetic quantum number. Magnetic quantum number was proposed by Landé, and it is denoted by ml. And here magnetic quantum number ml values starts from minus L, 0 plus L, followed by a formula 2L plus 1. 2L plus 1, which means that if you know the L value, then you can calculate the number of ml values. So for example, if L equals to 0, then the number of ml values are 2 into 0 plus 1, that is 2 into 0, 0 plus 1, 1. So if L equals to 0, L equals to 0 means what? S orbital. Then how many subshells present in S orbital? 1 subshell. Similarly, if L equals to 1, then the orbital is, if L equals to 1, the orbital is p orbital. So how many ml values will be possessed by p orbital? Let's calculate. If L equals to 1, then ml equals to 2L plus 1. 2 into 1 plus 1. 2 into 1, 2 plus 1, 3. So if L equals to 1, that is p orbital will be having ml values 3, whose values will start from minus L, 0 plus L likewise. Minus 1, 0 plus 1. These are the 3 values, 3 ml values for a given orbital. So this is how we can calculate the ml values for the one which you know about the L values. So which means that if you know the L value, then you can calculate its ml values followed by a formulaic expression 2L plus 1. So in this magnetic quantum number, you will be having an information about the orientation of the orbital, and at the same time the number of subshells present in a particular orbital. That's about the magnetic quantum number. S orbital has 1 subshell. S orbital has 1 subshell. P orbital has 3 subshells. D orbital has 5 subshells. Similarly, F orbital will be having 7 subshells. 1, 2, 3, 4, 5, 6, 7. So here, principal quantum number explains about the size. Azimuthal quantum number explains about the shape of the orbital, while the third one explains about the number of subshells present in a particular orbital. So S orbital has 1 subshell, P orbital has 3 subshells, D orbital has 5 subshells, and F orbital has 7 subshells. So these number will be perfectly, accurately will be given by a particular quantum number called magnetic quantum number. So degenerate orbitals. Orbitals which are present in a particular orbit. Listen carefully. Orbitals which are present in a particular orbit will be having same energy. Such type of orbitals are known as degenerate orbitals. Let us take the p orbital. P orbital usually starts from second orbit. See, let it be the nucleus, first orbit, second orbit, n equals to 1, n equals to 2, here the L values. So here first orbit comprises 1s orbital, second orbit comprises 2 orbitals, namely 2s, 2p. So 2p orbital, how many subshells are present in p orbital? 3 orbitals. They are px, py, pz. See here, 1, 2, 3, 2px, 2py, 2pz. Here should be very careful at the number 2. This 2 indicates about the second orbit. The second orbit, p orbital starts from second orbit, and the p orbital comprises 3 subshells, likely px, py, pz. These 3 subshells will be having same energy as they are present in second orbit. So the orbitals which are present in a particular orbit will be having same energy are called degenerate orbitals. సమశక్తి ఆర్బిటాల్ అని అంటారు అన్నమాట. ఒక ఆర్బిట్ లో ఉన్నటువంటి ఆర్బిటాల్స్, పి ఆర్బిటాల్ రెండవ ఆర్బిట్ నుంచి మొదలవుతుంది. ఇక్కడ 2 అనేటటువంటిది కాన్స్టెంట్, సెకండ్ ఆర్బిట్ లో పి ఆర్బిటాల్ స్టార్ట్ అవుతుంది. అందులో ఉన్నటువంటి ఆర్బిటాల్స్ ఏవి? పిఎక్స్, పివై, పిజెడ్. వాటికి సెకండ్ ఆర్బిట్ లోనే ఉన్నాయి కాబట్టి దే బిలాంగ్స్ టు సెకండ్ ఎనర్జీ లెవెల్, విచ్ మీన్స్ ద ఎనర్జీ ఆఫ్ దట్ పర్టికులర్ ఆర్బిటాల్ ఈజ్ సేమ్. సచ్ కైండ్ ఆఫ్ ఆర్బిటాల్స్ ఆర్ కాల్డ్ degenerate orbitals. And now the fourth type of quantum number is a spin. Here the term itself infers that it is the type of quantum number which is going to explain about the behavior. Listen carefully. This is the quantum number which is going to explain about the behavior of the electron in a particular orbital. So there is a huge interlink between each and every quantum number. First quantum number explains about the energy of the orbit, and the second quantum number explains about the type of orbital and the shape of the orbital, while the third quantum number explains about the number of subshells present in that particular orbital. While this is the type of quantum number which explains about the behavior of the electron. Among all the 4 different types of quantum number, which quantum number explains about the behavior of electron is the spin quantum number. It was explained by Uhlenbeck and Gauss-Smith. And this one explains about the spin of electron, which means in a particular orbital, any given orbital will be accommodated by only 2 electrons, among which the first electron and the second electron. First electron's spin is plus of, while the value of second electron is minus of, which means that ms values are plus of and minus of. If 2 electrons present in a particular orbital are with the positive values, then they are parallel with each other. If they are having plus of and minus of as the values, then they are anti-parallel. That's about the spin quantum number. So the most important thing that you should learn from the spin quantum number is, this is the type of quantum number which explains about the behavior of the electron in a particular given orbital, proposed by Uhlenbeck and Gauss-Smith. Let's have the schematic structure of all these 4 different types of quantum numbers and how they help us to understand about the behavior of an electron in an orbit and in an orbital as well in its subshell. The first orbit, which is very close to the nucleus, is first orbit. N equals to 1, n equals to 2, n equals to 3, n equals to 4. This is about the principal quantum number, the first quantum number, which explains about the size of the orbit, which also explains about the energy E1, E2, E3, E4. According to principal quantum number, E4 is greater than E3, E3 is greater than E2, E2 is greater than E1. As long as the electron moves away from the nucleus, the energy of the orbit will get increases. That's about the principal quantum number. And the orbitals present in each orbit. So first orbit consists of s orbital 1s. Second orbital consists of 2 orbitals. Here 2 infers that it consists of 2 orbitals. 2s, 2p. And here third orbit infers that it consists of 3 orbitals. There are 3s, 3p, 3d. So the newly joining orbital in the third orbit is 3d. Similarly, if you go for the fourth orbit, one other new orbital will be added. That is 4f. So 2p. P orbital starts from second orbit. D orbital starts from third orbit. F orbital starts from fourth orbit. So that's about the second quantum number and energy levels. Then we go for third quantum numbers. Let's have the values. N equals to 1, 2, 3, 4. 1 is nothing but K. 2 is nothing but L. 3 is nothing but M. 4 is nothing but N. And second quantum number is denoted by L, whose value starts from 0, 1, 2 and 3 and so on. So second quantum number explains about the orbital, the shape of the orbital. So here 0 is nothing but s orbital, 1 is nothing but p orbital, 2 is nothing but d orbital, 3 is nothing but f orbital. Similarly, third quantum number, whose value starts from 2l plus 1 minus l 0 plus l. These are the integer values of a third quantum number, which explains about the orientation of the electron in an orbital. So that's about ml. If you know the l value, then it will be very easy to calculate ml value. Fourth quantum number is ms. Whose values are magnetic quantum number, and it will be having a formula called 2l plus 1, whose value starts from minus l, 0 plus l. If you know the l value, then you can calculate the number of ml values. So orbit, orbital, subshapes. First quantum number explains about the size of the orbit. Second quantum number explains about the orbital. Third quantum number explains about the number of subshells found in a particular orbital. And fourth quantum number explains about the intrinsic property of an electron. So here an orbital consists of only 2 electrons. The first electron will be in the plus half direction, while the second electron will be in minus half direction. One is in clockwise direction, the second one will be in anti-clockwise direction. That's about the 4 different types of quantum numbers.